Next, let's derive the convolution integral in detail. For a linear zero-state circuit, if the excitation is a unit impulse function, the response is a unit impulse response. Now we want to solve the response with any excitation. According to the previous discussion, any excitation's waveform can be divided into several flat waves. These flat waves can also be seen as several pulse waves. For the first pulse wave, we think its height is the value corresponding to the leading edge time E0 specifically. According to lecture A1, we can easily get the expression of this pulse wave. Similarly, the second pulse wave is delayed delta tau, and its height is the value corresponding to its rising edge time. This is its expression. The rest can be deduced with analogy. For k+1's pulse wave, its delay and expression is like this. So we suppose k is from 0 to infinity and write out the general expression of these pulse waves. Next, we have to review how to change the pulse waves into the unit impulse waves. In lecture A2, we've discussed that only when the length of the unit pulse wave tends to 0, the function becomes a unit impulse function. In other words, under the condition that the area of the unit pulse wave is 1, when delta tends to 0, pt tends to delta t. The width is this pulse wave is delta tau. So it should time and divide delta tau simultaneously to form a unit pulse wave. Then we get this expression. The yellow part is a delay of the unit pulse function, which is made especially. It can be written as a form of pt and the delay of pt. In the deduction above, the excitation is thought as the sum of infinite unit pulse waves and their delay, times the corresponding coefficients. Every unit pulse function corresponds to a response. What's their sum? We suppose the response corresponding to the unit pulse function is a unit pulse response HPT. According to the property of the zero-state linear circuit, when the unit pulse function times a constant, its response times the same constant due to the homogeneity. The k+1's unit pulse function has a delay and times two constants. According to the homogeneity and time invariant properties, its response is like this. The time invariant property means when the excitation delays k times delta tau, the response also delays k times delta tau. So we know the response of the sum of infinite unit pulse functions is the sum of the corresponding infinite unit pulse responses. At time t, what's a superposition of the responses of the unit pulse functions before time t? We suppose there are n pulse waves before time t. So the number of the excitation is no longer infinite, but n. K is from 0 to n-1. We use waveforms to explain the response. The dotted lines correspond to the former pulse waves. We suppose the response of the first pulse is in this form. Obviously, the response of the second pulse has the same waveform as the first. It delays delta tau, and its magnitude changes linearly. Their sum is the response of the first two pulses. The response of the third pulse also delays and changes its magnitude linearly. The sum of the first three responses is the total response of the first three excitations. The rest can be deduced with analogy. By adding the responses of all n unit pulses before time t together, we can get the response of n unit pulses at time t. So the response of the whole system at time t can be expressed as a linear combination of the n unit pulse responses. It's because of the additivity property of the zero-state linear system. Next, we need to take the limit. We suppose the left of time t is divided into n segments. If n tends to infinity, delta tau certainly tends to d tau, and k times delta tau tends to tau. After taking the limit, the unit pulse function becomes their unit impulse function, and the unit pulse response becomes the unit impulse response. So the response can be written in the form of the integral. The lower limit is 0, and the upper limit is our interested time t. The expression of the integral can be written as this form. This is the lower limit of the integral corresponding to this. This is the upper limit of the integral corresponding to this. This is the first item of the integral corresponding to this. This is the second item of the integral corresponding to this. This is the integral variable corresponding to this. You can find RT is the limit of the sum of the responses when n tends to infinity. We need to point out that this expression includes tau and t. The tau is the integral variable, and the t is the time of the observation. In other words, the final expression of this integral is with time t. This expression is called the convolution integral of E and h, expressed in the form of E star times h. We need to point out that the solved response is a zero-state response with AT, because only when the zero-state circuit has homogeneity and additivity properties. This is a prerequisite of the convolution integrals deduction.